the answers to problem set 3, Newton's laws of motion. In question 1, mass given, acceleration given, net force is to be found, and net force is always mass times acceleration. So take the product of the two, you get it as 265 Newton. Remember that net force always means the resultant force, and it's always the product of mass and acceleration. In the second one, weight is a force, and it's always mass times acceleration due to gravity. So to find the mass, just divide, and you get the mass as 150 kilogram. Weight definitely changes, so on the Earth, since we know that the mass is 150 kilogram on the moon and mass never changes, take the same mass multiplied with 9.8, you get the weight as approximately 1.5 times 10 to the 3 newtons. So mass never changes, it's a constant. Weight changes from place to place because the acceleration due to gravity changes. Question 3. The force is 75 in one direction, 90 in the opposite. Friction is 12 newtons, and the normal reaction is up along the Y. The system of interest here is the third child. And the wagon. Net force is mass times acceleration, but here the net force along the X. Now we are only considering the force along the X. And 90 is in one direction, as you can see, while 75 and friction are in the opposite direction. That's why those two are negative. You get 3 Newton. That's net force along the x-axis. So acceleration is that force divided by the mass. And if the friction was different, if it was 15, then the net force becomes 0. When you put 15 here, you're going to get 75, as I'm showing it down here, get it as 0, therefore the acceleration is 0. The force is here, 800 Newton applied on this person, and friction in the opposite. So net force is 800 minus friction. Cross multiply and solve for friction. This product is 108, that is what you get here. Switch sides, and the friction is 692 newtons. B part is on the other side. Okay, here. Now the net force should be mass times acceleration. So rearranging, we can find the force applied. (932 Newton). All right. The first person was the system of interest for A, but for B, it's both together. Fifth question. Forces, weight acting down, tension straight up through the string. And so when you take the net force along the y-axis, you get tension up, weight down, there's no acceleration, therefore set it equal to 0. So the tension is 588. But now if there is an acceleration, then you use the same formula, but it's not equal to 0, it's equal to m times whatever the acceleration is. Taking it to the other side, mass is common, so taken outside, you get 678 Newton. Of course, the tension in the cord is increased because the person is accelerating now. Number 6, these are the forces along the x-axis. And when you take the net force, you always look at the situation and decide which one is the bigger force. In this case, caps F is the bigger force. That's why you take that force minus the smaller one and set it equal to mass times acceleration. You get 1.03 times 10 to the 3 kilogram is the mass. In the 7th, again, net force is F minus F. This time you have to take the mass of all three because that is the system of interest. Applied force is 1900, and now you have all the masses added together gives 1800, and then get 910. For the B part, you get this as the answer, 1110 Newton. 8th one, those are the forces acting. And whenever you have a situation like this, you look at that, this force is along the x, this is along the y, but this force is neither along the x nor the y. And net force along the x is 0. See, if the force is neither along the x nor the y, then you will have to resolve them. So you don't resolve this because it's along the x. Neither do you resolve this because it's along the y already. So you resolve the force that's neither along the x nor the y. So you get this as F cos 35, and this is F sin 35. So along the x, F cos 35 minus F is equal to 0. And that gives F as 73 Newton. In the 9th one, once again you have the weight acting vertically down. You have the tension in the rope acting this way, and you have the applied force. So here you see that this force is along the y-axis, but this and this force are neither along the x nor the y. So you'll have to resolve both of these. So you have to resolve T1 and T2. And when you do that, see, this system is not moving, so you get T1 sine 15 is equal to T2 cos 10, because this component is going to be T2 cos 10. This is dissolved, and this is going to be T1 sine 15. They must be equal to each other. That's taking the net force along the y-axis. On substituting the numbers for sine 15 and cos 10, that's what you get. And then when you take the forces along the y-axis, this is going to be T1 cos 15. And you have T2, which is also going to give T2 sine 10. T2 sine 10. So you have the component of T1 along this direction, which is T1 cos 15. You have the component of T2 also along this direction, which is T2 sine 10. But remember, T2 is 0.263 T1. That's why you got those two added up, because both are in the same direction. And together they balance the weight, which is 76 times 9.8. So, considering the net force along the x and the y, you get two equations. And when you solve those, you get the tension as 736 T1. And knowing the value of T1, just substitute into this, you can get T2 as 194. In the 10th question, weight acting down, tension acting up, net force along the y is T minus the weight, which is mg. So T minus mg. So tension is, this must be equal to ma. Okay. So T is mg plus ma. That gives 1.87 times 10 to the 4. Now if the acceleration is 0, then tension becomes equal to mg. Because this term becomes 0. If acceleration is 0.6, put that into the fundamental equation. But this time the motion is down. You see, that's what. So therefore, that's why it's minus a. Now, to consider how much it moved, you have to consider three cases. And the velocities in each part, the time taken in each part. For the first, you can use this equation, initial velocity is 0. That is why you have this. So you get the displacement in the first part as 1.35. And the velocity at the end of that motion is given by V1 is A1 times T1, because the initial velocity is 0. And during the second part, it's moving at constant velocity, so you just multiply the velocity with the time. Excuse me. In the third part, it is decelerating, and the initial velocity is 1.8. So now you add up all the three to get the total displacement. Which is 19.4 meter. And of course the final velocity is 0. Thank you.